All right, let's talk about calculus. But wait, before you get scared off by the formulas, let's forget all that for a minute. We're going to go on a journey to understand the simple, beautiful ideas behind it and how calculus gives us these incredible, unbreakable guarantees about how pretty much everything works. So it all starts with a question that sounds, well, impossible. Picture a wild roller coaster track. At any single frozen in time instant, how steep is it right there? A point doesn't have any length, right? So how on earth can it have a slope? This very problem is one of the main reasons calculus was even invented. So how do we tackle something that seems impossible? Well, you start with something you can do. Instead of 1 point, let's just pick 2 points on that curve. Now, if we draw a straight line through them, that's called a secant line. And finding its slope, that's easy. It gives us a pretty decent, kind of sort of average idea of the curve's steepness between those 2 spots. Okay, now here's where the magic starts to happen. Let's take that second point and just slide it along the curve, moving it closer and closer to the first one. See what's happening? As that gap shrinks, our secant line starts to pivot, and its slope becomes a much, much better approximation of the curve's steepness right at that first point. And this is the big reveal. What happens when that distance doesn't just get small, but when it gets infinitely small, so close it's basically zero? Well, just like the source material says, the line becomes the tangent at that point. Our secant line literally transforms into the tangent line, a perfect line that just kisses the curve at that one single spot. And what we just watched, that whole process of sliding the points closer and closer, that's the derivative. That visual journey is the definition. It's just the slope of that final tangent line. It's what we get from that whole limiting process, and it gives us the instantaneous rate of change at one single tiny point. Okay, so we figured out this amazing trick for measuring slope at a single point. But does it work for every possible curve you can dream up? The short answer, nope. For us to be able to find a derivative, a function has to play by a few rules. So here we have 2 ideas that are related but really different. On the left, you've got a continuous function. Think of it this way. You can draw the whole thing without ever lifting your pen off the paper. It can have sharp corners, that's fine. But to be differentiable, like the curve on the right, it has to be more than just connected. It has to be smooth. No sharp corners, no cusps. Differentiability is a much higher standard. And the source material really nails this distinction. If you can find a derivative at a point, meaning you can draw a nice, clean tangent line, then the function has to be continuous right there. But, and this is the key, it doesn't work the other way around. Just because a function is connected doesn't guarantee it's going to be smooth everywhere. The textbook example, the one everyone uses because it makes it so obvious, is the absolute value function. F of x equals the absolute value of x. Its graph is that perfect V shape. It's totally continuous, right? No breaks. But look at that sharp point at the very bottom, at x equals 0. You can't draw a single tangent line there. Which way would it point? It can't decide. So it's continuous, but it is not differentiable at that one spot. Okay, so now we have our big rule. For a function to be differentiable, it's gotta be smooth. And here's the really cool part. When a function plays by this rule, calculus offers us some incredible, unshakable promises about how it behaves. These are the calculus guarantees. So let's frame it like this. If we've got a nice, smooth, continuous curve, and we just look at its journey from some starting point A to an ending point B, what can we say for certain must happen along the way? What is absolutely guaranteed? Our first guarantee is all about finding a flat spot. This idea comes from something called Rolle's theorem. Now, for Rolle's theorem to kick in, we just need 3 simple conditions. Think of it like a checklist. Number 1, the function has to be continuous, no gaps. Number 2, it has to be differentiable, no sharp corners. And number 3, this is the special one for Rolle's, it has to start and end at the exact same height. If you can check all 3 of those boxes, here's the payoff. The guarantee is that somewhere between your start and end points, there is at least one spot where the derivative is exactly 0. To put it simply, if you go on a smooth hike up and down a hill, but you end up back at the same elevation you started from, then at some point on that hike, you had to have been walking on perfectly flat ground. And when you picture it, this makes perfect sense. A derivative of 0 just means the slope of the tangent line is 0, which means the line is perfectly horizontal.
Rolle's theorem is just a guarantee that if you start and end at the same height on a smooth curve, you've got to have at least one peak or one valley where things flatten out completely.
All right, time for our second big guarantee. This one is huge. It connects the average rate of change over a whole trip with the instantaneous rate at one specific moment. This is the amazing mean value theorem.
Let's make this super real. Forget math for a second and imagine a car trip. You drive 60 miles and it takes you exactly 1 hour, from the moment you leave to the moment you arrive. Easy math, right? Your average speed for the whole trip was 60 miles per hour. But think about it. You know you weren't going 60 the whole time. You sped up on the highway, you slowed down for a traffic light. So does the fact that your average was 60 guarantee that at some point, even for just one split second, you look down and your speedometer read exactly 60 miles per hour? The mean value theorem answers with a huge, resounding yes, absolutely. As long as your journey is continuous and differentiable, which, a car's journey is, it guarantees there was at least one moment where your instantaneous speed, your derivative, was precisely equal to your average speed over the whole trip. This table really ties it all together beautifully. The average rate of change, that's the slope of the secant line connecting your start and end points, your average speed. The instantaneous rate of change, that's the slope of the tangent line at one specific point, your speedometer reading. The mean value theorem just guarantees that at some point, the tangent line's slope will be perfectly parallel to the secant line's slope. So we've walked through these incredible guarantees, and they all come from these simple ideas of slopes and smoothness. But why does this foundational stuff really matter? What's the big picture here? Well, let's just recap the big ideas. First, we figured out how to measure something that seemed impossible, the slope at one tiny point, using the derivative. Second, we learned that to use this amazing tool, our functions need to be differentiable, which is just a fancy way of saying they have to be smooth. Third, Rolle's theorem promised us a flat spot if we start and end a smooth journey at the same height. And finally, the mean value theorem guaranteed us that at some moment, our instantaneous speed will match our average speed. And here's the final thought. These theorems might seem a little abstract, but they are the absolute logical bedrock that all of calculus is built on. They provide the certainty we need to prove even bigger ideas. So the real question is, if we can guarantee these simple, fundamental truths about curves, what incredibly complex systems, I'm talking everything from planetary orbits to the chaos of economic markets, can we now begin to describe, to model, and maybe even to predict with real confidence?